Hello, and thank you for tuning in. Thank you also to the organizers for organizing the summer school despite COVID, and a big congratulations for the 10-year anniversary. My name is Slav Petrov, and I work at Google. I co-lead the language team, and I'll be presenting the work of the team and of my colleagues. I'm actually not an author on most of the papers. I'm just have the pleasure and honor of presenting their work. So I've included references to all the slides, to all the papers, and feel free to reach out to all my colleagues if there are questions beyond what I can answer in the Q&A. But otherwise, I look forward to chatting with you at the end of the talk. So, as I said, this is the 10-year anniversary of AlexMLX, and I have been fortunate enough to participate in 9 of the 10 editions. I missed one the year I got married and was on my honeymoon, so I hope that counts as a valid excuse. But given the round anniversary, I thought it would be fun to take a look back, and actually it turns out that the website is still up for the first edition. And furthermore, you can see the, oops, let me turn on my pointer. Yeah. So you can see that already 10 years ago, I had the pleasure of giving the invited talk on Saturday night. Followed by the banquet, and followed by a lecture on the next morning by me about syntax and parsing. We learned from our mistakes. I think we were young and green and very ambitious to have a Sunday morning talk. Now there is a free day on Sunday, which I think is much more humane. So I took a look at my slides, and one of the examples that I used in my talk is from Fernando Pereira, who had used it at that time. A query that is relatively frequent and therefore perhaps could be considered easy. Painkillers that don't upset the stomach. Well, if you look at the results, they were actually quite bad back then. And there are multiple reasons for this. On the one hand, painkillers are a class of items, and we're looking for a specific instance of that class. There's a negation, which is notoriously hard to deal for IR systems, and then upset the stomach is something that can be said in many different ways. So it is not perhaps too surprising that we couldn't deal with it well, but the better language understanding ought to help. And so without having worked on this query specifically, I just issued the query this week, 10 years later, and was quite happy to see that we can actually get it right now. Stomach-friendly painkillers, gastroresistant naproxen aims to stop the devil, blah, blah, blah. So we've learned that stomach-friendly and don't upset the stomach are actually synonymous or paraphrases of each other, which is a fairly elegant way of dealing with the negation. And then we got lucky that the word painkillers is mentioned in addition to the specific brand name. But perhaps we might even know something about this is a relation that holds there. So let's take a look at the progress in some other areas. As I said, I was teaching syntactic parsing and working on syntactic parsing at that time. And so in my morning lecture, I showed a graph where syntactic parsing accuracy was in the low 90s, with human accuracy being considered somewhere around 97%, or in the annotated agreement on the Wall Street Journal tree bank, which was used for evaluation. Well, for a few years, there was not that much progress, but then in the last couple of years, we've seen tremendous progress, and we're now actually approaching human level performance on this now more than 20-year-old data set. So this is super impressive in my opinion, and perhaps as a result also explains why the focus has shifted away from syntax, which was never meant as a means to an end, to higher level comprehension tasks like question answering. And so we can take a look at the squat data set for question answering and notice that machines are now surpassing human performance. So human performance about 86, 89%, but machines are well above 90% on exact match and 93% on F1. If we look at glue as a benchmark with multiple tasks, we notice that the humans actually down here in 13th place. There are 12 systems that are better. And that might give you a pause and wonder, wait, like, what's going on? Did the humans kind of not focus? Are they not consistent with themselves and machines are learning to exploit that? I think it's a combination of multiple things. And this talk will hopefully shed some light on this. But one thing I'd like to point out already on this slide is that it's not really a fair comparison in the sense that the humans, like, they have one language processing capacity module in their brain, and they do all the tasks, while the machines, like, each role doesn't actually correspond to a single model, but we're tuning each model for each specific task. So there are different parameters settings that correspond to the different columns in this table. And as a result, I think we oftentimes end up overfitting to the idiosyncrasies of a specific data set and can get the machine to be very consistent in span boundaries and other things where humans might perhaps be a bit noisier. And that might explain why we get superhuman performance. In addition to the fact that the data sets are oftentimes somewhat synthetic in nature and allow for shortcut predictions, exploiting correlations that the neural models are really good at, while the humans are actually doing proper language comprehension to solve them. We'll get back to that point later. After glue, super glue came out with more tasks that are more difficult. And here, at least, we have the humans still in first place, but not by much. We're about 0.5% above T5. So I think these leaderboards have been, on one hand, very useful for driving progress. On the other hand, I think they've also led to too much focus on just numbers and too little focus on motivation, analysis, and understanding of what these models are doing. And I hope that I saw some trends at ACL that there's more work on evaluation, and that's why I structured the talk the way I structured it too, because I think we need more work on data sets and evaluation and not just on hill climbing on existing metrics. But nonetheless, like, this progress has been fairly real and is in big part due to BERT. Like, we had seen quite a bit of progress from word embeddings and neural representations, but then with BERT and derivatives of BERT, we've seen a quantum sort of step. And when people say BERT, they sometimes mean different things. So I thought I would go through and describe what I consider the most interesting parts of BERT. At first, it's, of course, the pre-training. Pre-training allows us to exploit large amounts of unlabeled data to learn something about language and about the world. In the past, especially like 10, 15 years ago, like, we used to just train models just on the training set for that specific task. And that is very limiting. There's only so much you can learn from a few 100,000 words. But if you have a few 100 million words or sentences, now you can start to really learn general purpose representations that then can be fine-tuned for the task that you care about. And to make this possible, I think on the one hand, like, we needed to get more compute power, and GPUs and TPUs have been tremendously helpful. But we also needed to adjust our models and the model architectures. So this one slide is meant to illustrate kind of self-attention transformers, but also not actually shows a little bit of the history of representation learning in language. So in sort of graphical models or SVMs, what we would usually do is take a word, each word, build a vocabulary, and map each word to a one dimension. As a result, the word vectors for different words were orthogonal with each other because they occupied different dimensions. And it was very hard to learn similarity between these words. So word embeddings project these one-hot vectors into a lower dimensional space where similar words occupy the same or similar parts of the search space, modeling space, and thereby allow us to generalize to words with similar meanings. And then we use these word embeddings in whatever neural architecture you want to do a prediction. A limitation of this is that a word that has different meanings will get mapped to the same vector regardless of how it is being used in that particular context. For example, the word book might be I want to book a flight, or it might mean I want to read a book. And these are two very different meanings, but the word embedding kind of conflates the two meanings, and the neural network then later needs to try to disentangle them. What self-attention and transformer does is it allows us to split the word representations and project them onto query, key, and value pairs, and then recombine them in a contextualized manner. So each word vector will be projected down onto these three separate vectors. And then when we want to compute, for example, the representation of the word bird in this cooking with bird phrase, we'll use the query projection and compute a dot product with the keys of all the other words to give us the weights of the other words, and then recombine them by taking the value of the other words, multiplying it by the weight that we've computed, the self-attention weight, and then summing them up to get the contextual representation of the word bird. As a result, we can have different representations for the word book depending on the context. And this modeling power allows us to really do much better language understanding. So much better than before that even the business side of things has taken notice. So, Sundar Pichai, Google's CEO, mentioned BERT in the earnings call last fall. I couldn't believe my ears when I heard that, and it was quite exciting and a great sign of how important and central this technology has become to the company. Pandu Nayak, who leads search, then also described how it's being used in search and the impacts that having kind of 1 in 10 searches is benefiting from BERT, and this is one of the biggest advances in the last 5 years, is what Sundar said. And this is real stuff that has been rolled out not just for English but for many other languages at this point. And so when you go to Google and ask who invented BERT, a BERT model is actually used to answer that question and sort of matrix style recursively give you the answer, Jacob Devlin. So this is pretty cool, and might make you wonder, well, okay, sounds like everything is solved. Like we are above human performance. This is used in production. What's left? Well, a lot is left. Otherwise, I wouldn't be giving this talk. Here's just one simple example. What song is Slav Petrov singing? Well, I'm not singing, but Google thinks that I am singing Kobe Niki. And the reason why it's thinking it is that it has learned to generalize and to drop words that might not be so important. And Slav is a pretty rare word. So seems like Victor Petrov is close enough. Well, in many other situations, this kind of replacing a rare word with a more frequent word that occupies the same slot and is of the same type is a good sort of superficial pattern to learn. But when it comes to names, it's not a good thing to do because it really changes the meaning. And that's something that we need more sophisticated kind of understanding to capture. And the talk will be yes, the answer is no, we're not done. And the talk will be structured in kind of 3 sections. I'll talk about data sets, evaluation, and then models for reasoning, trying to drive us to sort of towards deeper understanding and going beyond the surface correlations that we're currently oftentimes exploiting to get seemingly superhuman performance. So let's go back to the question answering example. And actually, even though squad is called question answering, I think it is really a reading comprehension task. And the difference is small and subtle, but really important. And I hope this slide will clarify it. In reading comprehension, you're giving a paragraph or a piece of text in general, and you're asked to create a question that can be answered from that paragraph, and then the question is shown to somebody else who needs to find the answer. While this produces question-answer pairs, it produces also a bunch of undesired side effects. Because you're primed by what is written in the paragraph, even if you try to use your own words, you're more likely to use similar words or grammar as in the passage. And as a result, the question will be very close in style and vocabulary to the original passage. Real-world question answering, on the other hand, is different. You don't know what the answers are, and you need to phrase your question in the way that's most natural to you. But the way that you phrase your question is different than the way that your cousin phrases their question. And it's also different than what might be potential answers on the web. So here, for example, what ship did Han Solo pilot as a question leads to a website that talks about the Millennium Falcon as a fictional starship. And then it says that Corellian light fighter is primarily commanded by Corellian smuggler Han Solo. So in order to find the answer, you need to understand that ship and starship are interchangeable in this context, and commanded can mean to pilot. So it's significantly more difficult for a machine learned system. For a human, the difference is maybe not that obvious or not that big, but it's much, much harder for machine learned systems. And as a result, the performance is much lower. So this is the Google Natural Questions leaderboard. We released this data set last year, and it's based on real user queries. So these are unbiased natural questions. Of course, we took the privacy of our users very seriously, and we made sure that the queries were issued for multiple accounts over multiple days from, actually not multiple accounts, from multiple locations over multiple days, and therefore are not things that are private to anybody. And there was aggregation and filtering for offensive terms and curation to make sure that these are good questions. We took questions where Wikipedia was among the top 5 website results, and then had humans annotate potential answers on the Wikipedia page. And in many cases, there was no answer. So we then just the system needs to say that there's no answer. And then when you look at the results, like they were in the upper 60s when we started. They've improved now, but we're still in the mid 70s, so significantly lower than what the accuracy on squad is. We also show precision recall and recall at fixed precision. And maybe a note here, recall at 90, I think is a very good number to look at because in order to build trust in a system, it needs to be sufficiently reliable. And 90%, I think, is a good goal to aim for. If something is 70% accurate, like 3 out of 10, almost 1 out of 3, questions will be wrong, and you won't trust it. But when you get to 90%, it becomes more reliable. And here, the recall is only 50%, 52%. So we have a long way to go on this data set. And I encourage you to take a look. We have a few 100,000 questions to train on, and then a development set as well as a blind test set. This is English only, but we care, of course, about other languages as well. And so as a follow-on, we released TiedIQA, which takes the same motivation as NQ, but in order to speed up the process and to do this for multiple languages, and without having to go through the expensive curation of queries, John Clark, the lead author of this work, came up with a very nice way of doing this by giving people access to a passage, but then asking them to pose a question that is not answered in the passage, but is interesting to and relevant to the context, and then finding other websites where this might be answered. And this yields, again, natural questions because you don't know how the answer is going to look like, but was faster to do than natural questions. And TiedIQA is also part of another benchmark that we recently released, Extreme, in collaboration with folks from DeepMind, on multilingual representations more broadly. In addition to question answering, there is also sentence pair classification, structured prediction, and retrieval tasks. Now, switching gears, beyond sort of the comprehension and understanding, I think it's also very important to look at generation. And generation has seen quite a bit of attention in the last couple of years and progress due to that attention. And the reason is that language models have become very good at producing fluent text, and we're now thinking about how to get the models to be factually correct and to avoid hallucinations. And while summarization is the standard generation task, perhaps, I really like the more structured input setting where you know exactly what information you need to verbalize. Because in a summary, it's quite subjective. What are the salient parts? And different humans might write different summaries. But if I give you a table and point at a cell or a row and tell you what is written there, like, the information is in structured form, and you can clearly evaluate whether the model was faithful to the source and produced what was given as information and only what was given as information, and then whether it was also fluent. And so to this end, we have released this table to text generation set where we went through several rounds of iteration to take natural sentences and then remove information that was not available in the associated table to make sure that we have the minimal sentence that can be generated from the table, and that can be used for training systems and evaluation. All these sets are available, these data sets are all available on this GitHub repo, and there are several more. I encourage you to take a look and play with them. All right, so now switching gears a little bit and going from data sets as task definitions to more the annotation process and the evaluation also in particular. All of these data sets that I talked about, we use humans to annotate the data and give us the ground truth. But what is really ground truth? And is there such a thing as ground truth? I think, sadly, that it's a bit of a myth, and that we oftentimes wish we had ground truth, but it's actually much more complicated than this. So here's a sentence that's supposed to answer, or a passage that's supposed to answer the question, who was the first person to see Earth from space? And the potential answer is Yuri Gagarin was a Soviet Air Force pilot and cosmonaut who became the first human to journey into outer space. Now, some users or humans, annotators, said, yes, this is an answer. Yuri Gagarin was the first person in outer space, and he saw the Earth from outer space. And some others said, wait a second, it doesn't say that he actually saw Earth from outer space. It says he was in outer space. But we don't know whether his capsule, the Vostok 1, actually had a window and whether he looked out of it. And so if you ask me, like I would say, yeah, sure, he saw Earth from outer space when it's in a casual setting. But if this is in court and a matter of life or death, well, I cannot exclude the possibility that he did not see Earth from outer space, so I might annotate it differently. And the capabilities of our language understanding models have become so good and so fine-grained that these types of distinctions are starting to matter when we do the annotations, because the easy stuff we get most of the time right. And so we then said, okay, well, instead of getting 5-way annotations, what if we got 25-way annotations? Would we get like a clear winner? And it turns out yes and no. Like, so if you look at these charts, for 25-way annotation for long and short answers, we see dark green is definitely correct. Light green is correct but debatable, and red is the small bar at the bottom. So we see that there are fairly few really wrong answers, but the correct but debatable part is making up a significant part of the distribution, and the mode of the distribution is only at about 60%. So it's not like 90% of people agree. For many questions, people have quite a bit of a spread. And so based on this study on question answering, we doubled down, and Tom Kwiatkowski, together with Eli Pavlik, looked at natural language inference. But before we look at the results, let's take a step back and kind of just remind ourselves what is natural language inference and what is entailment. Well, in semantics, kind of in the school of Montagu, like semantics is all about entailment. And the definition is that the premise P entails the hypothesis H if in every possible world in which P is true, H is also true. But that's pretty hard to kind of do in practice and to enforce in practice. So oftentimes what we do in practice is a little bit more kind of flexible. We say that P entails H if typically a human reading P would infer that H is most likely true, assuming common human understanding of language as well as common background knowledge. This is something that Ido Dagan said in 2006, and I think that still holds to this day. But he also said the task definition and evaluation methodologies are clearly not mature yet. We expect them to change over time. And I don't think they've changed enough, and maybe it's time for them to change a little more to take into account the human factor in all of this. So if we look at this premise, a young woman stands by a barbecue, and the hypothesis the young female is near a machine, we see that there's quite a bit of a varying interpretation. Most people say this is neutral, and close second is the group of people who say that there's an entailment relationship. But it's very bimodal. And when you look at sort of 50-way annotations of a large number of sentences, you find that a simple Gaussian is actually not a good fit for the data, and it's much more of a mixture of Gaussian distribution. And I refer you to the paper to take a look at the really nice analysis and examples that are there. But sort of to kind of cut to the conclusions, like we chose to take the easy route in the annotations and to not be prescriptivist. But that meant that we would need to be more careful in the evaluation. And we haven't really been that careful in the evaluation. I think we've just taken the majority as the truth, rounding the rest as noise and human errors. But it's not human error. It's just different understanding and nuances of how the world and language is interpreted. And I think we need to embrace this. And one way forward might be that we evaluate on the distribution. Um, but longer term, I think we need to have models that can rationalize and explain their reasoning rather than just producing a one-bit answer. And switching gears to text generation again, text generation is notoriously tricky to evaluate because it has this chicken and egg property that if you know how to generate fluent text, then you can use that technique to also evaluate your model. But if you don't know how to, but if you can evaluate text, well, then you can use that technique for generating text in a loop. And so we've been stuck a little bit between human annotations that are expensive but accurate and automatic metrics, which are quick to compute but inaccurate. And in the last couple of years, there's been a bunch of activity about hybrid metrics, trying to do learning and model-based approaches. Our proposal, my colleagues in New York, is to combine the power of BERT and use ideas from Blue to learn a metric that is robust but flexible. And so in a nutshell, the idea is that we'll take a standard pre-trained BERT model, but then we will do additional pre-training on synthetic data that is generated just for the task of generation. So what we'll do is we'll do fill in the blank where we will fill in different words, and then we'll use Blue and Rouge and other automated metrics to compute a score, and we'll train a model to predict that score in a multitask way. And so here on the slide, we're showing kind of Blue, Rouge, BERT score, a bunch of other things, back translation, entailment that we talked about. And so basically we'll take raw sentences from the web, we'll perturb them, and then we will evaluate them according to automated metrics and train the model to be able to predict all of these things. And so the representations of this model ideally would be then robust and useful for different types of evaluations. And we can then fine tune them on machine translation or on other tasks. And this works impressively well for machine translation, as shown on this bar graph, outperforming other generation metrics that have been proposed in the past. Cool. So now this brings me to the fourth part, models for reasoning. Do we need new models is I think, a fair question. And it might be interesting to run a poll in the research community. And I suspect you might get different results whether you poll people from the NLP community or from the machine learning community. I think many machine learning people are believers in just bigger models will be sufficient. And this line of work from the Google Brain team, I think is super exciting work of just trying to map everything into text-to-text models. You have one big multitask model, and you can put in strings as an input, and some demarcation gives you an indicator of what task you're trying to solve, and then out comes a string, linearized string of the output. And you can pre-train this on a lot of data and then fine-tune it for the tasks that you care about. It works remarkably well for a bunch of things, and it's quite surprising how well it does. But it is also very expensive to train, and was sort of state of the art in terms of size for a while until a couple of weeks ago. OpenAI released GPT-3, which is probably the biggest model that's out there. And it follows sort of the same premise, but perhaps adds a spin on saying that the goal is to do few-shot learning. The idea is you train a large language model, and then based on a small set of labeled examples, you can fine-tune it for the tasks that you care. I'm super excited about this paradigm of multitask training with different tasks, and especially tasks with more data, help tasks with smaller data. And then few-shot learning, where we are able to benefit from representations that were learned on large amounts of unlabeled text. But I have some concerns about the specific kind of results and how kind of realistic things are. So as we talked about before, for something to be useful in practice, I think it's good to be close to 90% accurate. And if I look at this plot here at the top, like as we make the model bigger, and this is a logarithmic scale, like we're not plateaued, but we're also nowhere close to 90% accuracy. And so 0, 1 shot, few shot, like there's a significant difference, but like I think the few shot setting is still too weak of a supervision. I would like to see a many or a few more shot learning examples and see whether it's possible to actually extrapolate and get to 90%. And also once you get to 90%, how much data have you saved compared to previous approaches, and does it justify building such an expensive model? Because if we look at the compute, which is down here, BERT is all the way on the left, and GPT-3 is all the way on the right, with about 1,000 times more compute. So BERT is already expensive to train and hard to replicate in an academic setting, but this is 1,000 times more expensive. And I think it's important to explore these things, but it gives me also pause and makes me wonder whether there aren't more efficient ways of representing knowledge. Because if you think about it, like everything that this model learns influences its parameters in some form. But so there might be a sentence out there on the web that has my birth date or my phone number. And GPT-3 might see it in its training, but would it be a good way to use its parameters to store that information? And how do you know what information to store? It would be perhaps more efficient and certainly more inspectable if the memory was kind of factored out of the model and we could have representation for the language and a representation of the world knowledge separately. And so this line of thinking is, I think, closer to what I envision as a productive way forward. And we have several papers in this space. So all of them kind of have this premise that like language models capture linguistic information as well as world knowledge information about the world. And they kind of mix the two. So if I look at this example, he said he blah blah eaten the asparagus. He had eaten the asparagus. That's something linguistic. On the other hand, we paid 20x at the Louvre gift shop in order to fill it in. Like a language model might figure it out just based on Louvre. But on the other hand, if you really wanted to kind of construct the answer, you would need to know that the Louvre is in France, and in France is the euro is the currency, and you use currencies to pay. So this might be kind of a lot to ask for, but there might be some intermediate kind of piece of information that you can look up. And so I won't talk about the realm work in detail because Christina Teutonova, who is a colleague of mine at Google, gave a talk yesterday, and if you haven't seen it, I highly recommend that you take a look at it, where she described this line of work. Basically, the idea is that rather than trying to predict and fill in the blank out of kind of from your memory, you're allowed to do a lookup. And this is kind of like, and retrieve a piece of information and then condition on that piece of information, that piece of text, fill in the blank. So it's basically the difference between open book and closed book exam. And but only one lookup allowed in the book. And so I think it's a more realistic way of dealing with things rather than requiring everything to be in the parameters. And it has the nice side effect that you don't need an explicit knowledge representation. Everything stays in the text space. You're retrieving text and you're reasoning over text without having to come up with an abstract meaning representation. It does a little better than T5 with a much smaller number of parameters. But of course, it's a kind of open versus closed book exam settings that sets these two apart. So it's not a really fair comparison. And overall, the numbers are still fairly low. But I think it's really exciting that you can actually do these conditional language models where you can train a representation and use use it to learn retrieval at the same time and on the fly update the index asynchronously. It's quite a feat of engineering and just machine learning to get it done. So I definitely encourage you to take a look at the paper. But another line of work that we've been pursuing is what we call entities as experts. And as we saw in the example with Slav, Petrov singing, entities are somewhat special. They're not just strings. And so it might make sense to have an explicit memory that is centered around entities and information about those entities. And so here the idea is that we'll have our regular transformer architecture, BERT architecture, but in addition, we'll have a memory where we have embeddings that we can look up as site information. Of course, in order to do the lookup, we need to ground strings in the memory, and so this is akin to entity linking. And so what this model does is actually it's a multitask model that can do mention detection and then entity linking to the knowledge graph or to the memory, and then do prediction based on this information by combining all the information that it has access to. And this is a paper that's currently in submission. That was then extended further to include also facts, because having a vector that you can look up per entity or a set of vectors and that you can attend over is good as site information, but perhaps we want to be a bit more structured and not just look up an entity, but also look up an attribute or a relation. And what the facts as expert work does is it takes entities as experts structure shown here on the left. It's just a different visualization, but it's the same idea or same model. And then in addition to that, it has a fact memory. And now the fact memory is keyed not by just one vector, but by two. You have the subject and the relation, and that allows you to look up the value, which is the object of the relation. And so this allows you now to bridge quite nicely between structured information sources and unstructured information sources. Of course, this is just the first step in that direction, and there's more to be done, but I think this is a really rich area for future research because we have a lot of information in structured form, and BERT and GPT-3 and other models are not really using it. One other line of work that sort of goes even beyond the facts as expert in a way, but on the other hand is based on a very different architecture and predates it. It's this work by Bu and Dinger that was presented at iClear earlier this year. And it's about multi-hop reasoning over unstructured information. So typically multi-hop reasoning will be done in the context of a knowledge base where you can follow the graph structure and look at the information. But here, what the authors do is they construct on the fly something like a virtual knowledge base that allows you to do multi-hop reasoning based on pure text and unstructured information. I don't have time to discuss this work in detail, unfortunately, but here below you have the link if you wanted to take a look. So these were kind of the few types of models that we're exploring that go beyond just pure language models. We're also doing interesting work on the generation side to generate factual and faithful pieces of text without hallucinations. But in the interest of time, I'll just jump straight to the conclusions. Oh, no, actually. I will jump to one other type of reasoning, which is just doing a little bit of math. Um, this is something that is being explored in the DROP dataset, which was released by the AI2 Institute. And the idea here is that given a paragraph with some numerical values, you're supposed to reason and deduct some information that oftentimes requires some simple math. So in this case, the question is how many yards do the first 2 field goals converted add up to? One thing you'll notice here is that the question is quite long and a bit cumbersome, maybe not supernatural, and it is because it was generated based on somebody reading the passage, and so it has all these artifacts that I was talking about before. But given that the focus here is not just on extracting spans, but actually combining spans and reasoning over information, I think that's okay, because it forces us really to focus on the more math part. So in this case, one would extract the 2 spans about the first 2 field goals, 53 yard and then 44, and then I would need to add them up. Okay, my battery's empty, so we will stop. Okay. And so once you've extracted these spans, you need to add them up. And in general, the model will need to reason over a set of operators that are shown on the next slide once I get there. Okay, so we treat this as a structured prediction problem where we extract spans and intents, but the intents are the operators and the spans are the arguments to these operators. And then we execute these operators to produce the final answer. Of course, there can be multiple ways of producing an answer because different spans combined with different operators might yield the same result. And this type of spurious ambiguity is something that the model needs to learn to disambiguate. We use beam search and compare to reinforcement learning and other techniques in the paper. Yeah, so here are a set of operators. So as I said, like these were just sort of a quick whirlwind through a bunch of sort of more structured and articulated models that we are exploring, in addition to bigger language models. And to conclude, I think it's objectively fair to say that there's been a tremendous amount of progress in the last years, but we've also cut some corners which have made the progress perhaps appear faster or bigger than it actually is, and can lead us to believe that we can do things better than humans. I don't think we have any systems that can do things better than humans at this point of time. It's just that oftentimes the tasks, the data sets are easy or have systematic biases that these neural network models are just very good at exploiting and finding shortcuts to compute the correct answer without actually solving the task. And oftentimes our evaluation metrics are too simplistic. So going forward, I think we should embrace the inherent ambiguity in human judgments and use that to our advantage, both at training time, but especially at evaluation time, to build models that we can evaluate more accurately. And I think we need models, we need more efficient learners. And here efficiency comes in 2 flavors. One is fewer compute cycles, but 2, also fewer training examples. I think we are oftentimes brute forcing things right now. And with some more inductive biases in the models, we might be able to get away with fewer training examples, which would allow us to adapt to new languages and new domains faster. And finally, I didn't get to talk about this, but there's another invited talk on interpretability. I think trustworthiness is going to become increasingly important. And what I call trustworthiness is a combination of interpretability, fairness, and robustness. And we need these models to have all of these characteristics because they are becoming part of our everyday lives, and we need to be able to inspect and understand what they're doing and how they're making their predictions so that we can correct for biases that are out there in the world because they're trained on web data, which is biased by human perception, by human prejudices. And as we become more enlightened as a society, and we need to be able to advance our models along with us. So with this, I will stop, and I'm happy to take questions. Thank you very much for your attention.
Okay, thanks very much, Slav, for a wonderful talk. We're going to now start with the questions. We are going to be led by the monitors. I just wanted to solve one little mistake I made, which is I didn't introduce you, right? People might have heard from our conversation that 10 years ago, you were 1 year into Google, and right now you're co-leading the Google AI language team. So for everybody that doesn't know, I think most of you know already, when Slav talks about these things, it's things that he knows a lot about because he's leading those teams, right? So then we can start with the questions now. Alessio, do you want to lead the questions, or I can
do it? Yeah, I can do it. So there's a first question here is, as the efficiency of these models are increasing, the computation costs are also increasing exponentially. For example, with GPT-3, Google itself has provided many resources as Google Colab, etc. But do you think that there should be more focus on the trade-off between computation costs and performance?
Yes, it is a very good question, and I fully agree. I think it's really wrong that when we write papers, we report only the top-line accuracy, but we don't take into account the computational cost of the model in any way. And I think it's much more meaningful to actually have a two-dimensional plot where you have accuracy and computational cost, and there's oftentimes a trade-off. And we did a bunch of that kind of line of experimentation in our parsing work back in the day, and we tried to push the community to take efficiency more into account. It's kind of didn't really catch on, unfortunately, and I think it would be important to think about how to get people to think about this, because also some of these models we might want to run them on a phone device, and phones are quite powerful these days, but still, of course, like don't have the same resources as what one would have server side, and so being able to say, well, I can get within 1% of accuracy with 100 times less compute, I think it's a very impressive result, while getting within 1% of accuracy with the same amount of compute is maybe less impressive. And so I think it would be important to think about how to report these things. The challenge becomes often that implementation details matter, and sometimes academics might say, well, I didn't optimize my code, so it's not really fair to compare. But I do think that we need to pay more attention to the computational cost of the models.
Another one is if there's a mechanism to deal or avoid a bias, for example, gender bias.
Stay tuned. I mean, I think many people are working on it, and we are actively working on it as well. I think it is a very kind of important but also difficult area, and easy to get wrong as well, in the sense that I think sometimes we stay too much at the surface and don't really treat the underlying causes. So what I mean by that is that ideally we would have a causal model where we can say gender shouldn't be playing a role in making a decision. But most of our models are not causal. They just model correlations. And then we might come up with a heuristic way to measure a potential gender bias. And then sometimes it is tempting to use the same heuristic and augment the training data to fix that problem. And then, of course, on that specific evaluation, we're going to do much better. But we haven't really done much because we have just used a heuristic way to measure the problem and then the same heuristic way to fix it. And I think we need to have techniques for training models that are completely agnostic of the problem that we're trying to solve, because otherwise we'll just kind of surgically remove that specific instance or nuance of gender bias, but not necessarily solve the whole class of problems, because gender can be conveyed in many ways. It can be conveyed in pronouns, in names, but also implicitly in other things. And I think we need a lot more work in that space.
This one is about clarifying what is the N-way annotation of answers.
So this is the 25-way annotation remark that you did, the annotation disagreement.
Yeah, so basically what we did is we asked 25 people, given a question and a Wikipedia page, to find the answer and to mark it up. And so then we compared the 25 answers that were provided to us as in terms of the overlap they had, whether people chose the same section, whether they actually identified the same short answer. And we had experts, so people who were the co-authors on the paper, evaluate whether the answer was correct or whether it was kind of correct but debatable or incorrect. And so yeah, basically, like, we just repeated the same thing with the same task with 25 annotators.
Okay, next one. As the machine learning systems are overcoming human level performance, the evaluation becomes harder. So the question is how this problem can be tackled.
Yeah, if you have an answer, come talk to me. I mean, I think that's why I said, like, I think we need just more work on evaluation metrics. Like, I think in the past, we have sort of had two dominant approaches. One was sort of like a rule-based thing, something that can be deterministically computed and measures like accuracy, precision, recall, things like that. And then human evaluation, where a human looks at the output and vets it. And I think we need to go beyond that. We need to have multi-way human annotation, so kind of not just one human annotates or verifies the answer, but multiple people, because different people might interpret things differently, and this distribution matters. And then the other thing is that I think we need to do more on the hybrid front, where we have metrics that are computed by a sophisticated model, not by a deterministic process, and as a result might be kind of a bit noisy, but can be then supplemented with human judgments or fine-tuned with human judgments. Because if we just ask humans to label things, it's going to be very expensive and very slow, but the automated metrics that are kind of deterministic are not sufficient. And that's why we think that our computer systems are better than humans, but they're actually not.
Okay, one more here. Regarding memory and word knowledge, if we try to remove that from the models and perhaps make them more modular, which is your idea? How do we approach this? Sorry for this.
No worries. I have a small baby next to me as well. I mean, I presented a couple of approaches that we are currently pursuing. The papers are on archive. This is kind of very recent work, and there'll be more coming. I don't have the answer. I'm just kind of pointing out that I think this is an interesting area to look at, and I'm also happy to be convinced otherwise and to be proven wrong by people just building big models that don't need to disentangle the two. But I think we need to think about this this more.
There is one more question. So I deduct from your talk that learning BERT is a must for anybody wanting to dedicate to NLP. And would you say so? Or what are other must things to learn?
Yeah, I mean, I think BERT is a kind of, there are lots of tutorials on BERT that explain it, and so I think understanding sort of the space where BERT, kind of how BERT originated, what it is about, and how it works, I think is important. I'm just checking on Scholar how many citations it has had in the last since it came out in like a year and a half roughly, because they increase by the hundreds every week or so, and I think there will be a model passed after BERT. Like it's not that this is the final model. It's just one way that we know kind of right now to structure things, and that is fairly general purpose. But over time, I'm sure new things will come up, and I think for people wanting to get into NLP, it's not so much just about knowing BERT, but I think acquiring the intuitions of kind of what is important and how do we use math and neural networks to express our ideas, because then you'll be able to stay up to date on whatever comes after BERT. Yeah, so 8,000 citations in a year and a half, less than 2 years. So yes, a lot of work is based on that, and you want to do it, to take a look at it, but I don't think just kind of applying BERT to everything is the right solution. I think it's more about understanding the intuitions and how it is helping us kind of drive things forward.
Thank you. There's another question. Someone is asking about computational resources. So how many instances are needed to fine-tune these models satisfactorily?
I mean, you can kind of, I think one of the reasons why BERT is so popular is that there are differences between hyperparameter runs, and it's not to be neglected, but at the same time, there are many parameter settings that give you pretty good results. If you look at some of the follow-up work like Roberta and Albert, or kind of SpanBERT maybe as a better example, there are modeling innovations, but a lot of it is also just training BERT longer, tuning the hyperparameters, running a bit more, using more data. So even the BERT model itself was not perfectly tuned, but it was already so good that it kind of didn't matter that much. And so I think once you have a starting point that is so powerful, you don't need to run that many hyperparameter runs anymore. To get to that to that first model, you do need to run a bunch, but I think you also want to be smart about how you run an experiment. So the people on my team who are the most productive are actually very smart about how they run their experiments and how they use perhaps 10% of the training data to see kind of how is the learning curve looking like, and tune the parameters on a smaller amount of data. And then once you are in the right region, then you start training the big model on the large amount of data, rather than starting from scratch to optimize parameters for a giant model on all your data. And so you want to kind of bootstrap, start with a small model, less data, figure out roughly what the range of hyperparameters is, and then iterate.
So there is also a question about few-shot learning. Like, what is this reasonable amount of data of samples for few-shot learning for pre-training models?
Sorry, I didn't catch the question. Can you repeat?
I think this is more or less the same, right? This is basically the same question.
Yeah, how to quantize that small amount of data for pre-training?
What that means, small pre-training. I mean, that's why I said like it depends. Like I think 0 shot and 1 shot are clear. Once you go to few shot, I think there's a bit of a misconception perhaps in how things might work in practice, in the sense that if you have a training set, you can just hold out arbitrary amounts and you can say, well, let me see what happens with 50 examples. Let me see what happens with 100 examples. But in practice, when you're coming up with a new task, actually coming up with the guidelines of how to annotate examples is a big fixed cost. And so if you spend a day trying to define the task, then you might as well spend the day annotating examples and not just an hour. And so I think the setting where you just have 10 labeled examples is somewhat unrealistic, because you need to spend a bunch of time thinking about how you're going to annotate those examples. And you want to spend the same amount of time probably annotating examples, at which point you probably can have 100 or 500 examples. And if you really care about the task and the performance, like you might even go to 1,000, but the hope is that then with 1,000 examples, you can get to 1,000, like 90% accuracy or above. If 1,000 examples still get you only to 70%, then I think we haven't really moved the needle enough, and we need to work harder on the sort of few shot setting. Right?
So then there is a question about, do you think the availability of training data will continue to increase? Will there be constraints of the kind of data that learning models are able to access? And should there be those kind of constraints?
I mean, I think we haven't harvested kind of nearly all of the data that's out there. I think what I mentioned in the talk, like we used to just train on the training set of the, for example, Penn Tree Bank with 1 million words and try to learn a syntactic parser from that. And that was super hard. And now that we use pre-trained models, we can learn from a lot of unlabeled data. But this unlabeled data is all textual data. And if you think about how humans learn, like I have a baby and he's certainly influenced by what he hears from me, but he also interacts with the world and sees things. So I think multimodal and multitask learning will be will play a big role. And so collecting language and image data and learning models, pre-training models in an unsupervised way on multimodal data, I think is something that will give us big advances, but it is computationally quite expensive. Like in a few years, hopefully, we will be able to do these things more easily. But the BERT model, for example, like having a softmax over your vocabulary size, when I was in grad school, was just like conceptually you could think of it, but in practice you couldn't run it. And so I think with some of these multimodal ideas where we want to combine language and image and videos, we have ideas, but it's computationally too expensive even with big compute resources. And so as compute becomes cheaper, I think we will figure out how to harvest even more of the data, because most of the bits that are out there and bytes that are used for storing information on the web are not for text, they're for images and other things.
Okay, so another question about low resource languages. So a lot of advancements have been done in NLP for English. But how do you think those NLP tasks can develop in other languages with less training data? And which steps should we follow to develop in those directions?
I mean, I think we need to do more work in that space, and that's why I highlighted some of the data sets that have been made available. But beyond that, I think depending on kind of how low resource the language is, I think it might make sense to also completely rethink how we approach things, rather than sort of, in English, we have somewhat of a pipeline approach where we do speech recognition first, and then we do sentence segmentation, and so on and so forth. And there are clear word units and word boundaries and so on. But if you're building a system for language where you don't have a big web corpus and a big language model that you can use for a better speech recognizer and for pre-training your NLP model, perhaps it makes sense to rethink the whole pipeline and start directly from audio and go to interpretation. But then also to think about what are the tasks and the meaningful units or building blocks that we want to build. And I don't have the answers, but this is something that we are starting to think about more actively as we want to kind of provide language understanding capabilities in more and more languages.
Okay, so the last question for today is about models like BERT and GPT-3 are based only on language models. Do you think that this type of models could make use of language features like parse trees or named entities?
So I think it's a very good question. And in sort of, if you had asked me like 2 or 3 years ago, I would have been very kind of, I spent a lot of time working on parsing and sort of the classic NLP pipeline, and for many years tried to infuse neural representation with these linguistically motivated structures. But I think we've reached a point where the models are implicitly learning these things from raw data, and that's why they're so good at being fine-tuned for parsing or NER or any other task. And there might be small gains to be had for specific tasks, but overall, I think the models are discovering them for the most part. And the important thing is that the model structure, with self-attention, being able to attend to every term in the sentence, it sort of captures anything that you would pass along a parse tree anyways. Maybe it's a bit brute force and expensive because it's looking at all words all the time, while a parse tree would allow you to zoom in on specific things. But parse trees are also noisy and have errors, and so this allows you to kind of defend yourself against that. And so right now, I'm not very optimistic that there's much value to be gained from sort of forcing linguistic intuitions into things. And maybe sort of I'll end on a somewhat philosophical note. Like, if you think about how we learn to build airplanes or objects that fly, like when we try to imitate birds, we failed. But once we understood the underlying principles and the aerodynamics of it, we were able to build planes that follow the same principle as the bird wings, but actually work differently. They don't flap, we just use acceleration in another form. And so I think linguistic theory, sometimes we're in the same space. And if you come with a prescriptive notion of like, this is how it has to be done because linguistic tells us that this is the case, I think we will limit ourselves in unnecessary ways. But on the other hand, if we can build models that work well and then we inspect them and find linguistically meaningful patterns, then I think that can give us confidence that we're on the right track because the models are doing things that humans and linguists have discovered to be kind of useful abstractions. So I would rather have the things come out of the model than we put in at the beginning.
That was the end of the questions. Yeah, thank you a lot for addressing them.
Let me just say a few words. So first of all, thanks for the great talk, Slav. As you said in your presentation, and as Ramon reminded, you have been a speaker at LXMLS for all these 10 years. So thanks a lot for all that. And by browsing through your talks, it's amazing to see how much progress happens in NLP and how much it evolved. Sometimes in directions that were quite unexpected 10 years ago. So my question for you is, can you speculate a little bit about what could be your talk in 2030, like 10 years from now?
Thanks, Andrzej. I don't know. So what I like when I kind of do planning at work and with my team, like I like to challenge people to plan in 3-year increments. 1 year, you can just extrapolate from what you're doing, and you won't be able to do that much exciting stuff because it's too risky to propose something very speculative. 5 years and beyond, you can say whatever you want, and nobody will ever hold you to that because the world changes so fast. So 10 years is definitely outside of my comfort zone. But what I would hope to see, and perhaps that might mean that I need to actually change what my team works on is, I do think that in 10 years we'll have a lot more multimodal and multitask work. That this strict division of language, speech, vision, robotics will start blurring more, and that these different modalities will enhance each other. But how exactly the models will look like, whether we'll be still doing neural networks or we'll be doing something else, it's really hard to predict. I think it's what I've seen kind of the people who do well tend to be the ones who have a plan, but then when they see an opportunity are happy to throw the plan overboard and adjust their plan and don't stick too long and worry about sunk costs, but just move on and embrace the change and work on making their own work obsolete rather than trying to defend their work and say, no, but this line of thinking is the right thing. And so when we see progress, we just need to jump on it and move on. But yeah, I don't know. I think multimodal and multitasks are things that we all hope will give us advances. And so far, I think we have not really seen it much. Like we end up doing better when we're unimodal and fine-tuning for just one task. And so I hope that we can make some progress there.
Awesome. Great question. So I think that for today, that's kind of enough. We're 20 minutes over time. But probably I'm sure people will stick around at some point. You know, we have these virtual environments where we try to meet. So maybe during the week, there's also an opportunity at some point, if you had the time or to talk about this, or maybe with other speakers. But other than that, I would close here. Fernando, do you agree? Could we, you're hosting the session, right? Could we close the session here?
Sure.
Okay. So yes,
thanks everybody.
Thank you very much. Super interesting, and have a nice day. Bye, guys.
See you. Bye-bye.